It's my pleasure to start here Alan Smetana, who is, good afternoon, here Alan Smetana, collaborator and friend, who is going to give us a seminar today. He's going to talk about our interferometry of neutrino electromagnetism.
Thank you very much. So thank you that I can speak here again after some years that I was not here, and I try to use mouse as a pointer. So I hope that everybody sees it. Like here we see it in Zoom. I hope also. Otherwise, you can write a message to Antonio in the Zoom if there's some problem. So I'm coming from Czech Republic, from Institute of Experimental and Applied Physics of Czech Technical University in Prague. And this work, what I am going to talk here, is my recent work together with my PhD student Maria Petropavlova. And it is available in the archive, but it's also recently it is accepted for the PRD journal. So last proofs were already made, so we expect to following few days to have it available online, but I don't know the number yet. So first, let me go to this slide, which is basically it's a cosmological slide, which motivates why we should or why we can or would like to maybe be interested in such thing, what was in the title, like neutrino electromagnetism. And this is like a very simple motivation, because if we look at the universe as the whole and its evolution, then we, in standard cosmological model, we end up with such diagram where we have evolution of different parts of energy density budget of the whole universe. So here we have baryons, how they evolve, cold dark matter, neutrinos, and photons. So you can see here that at early stages it was dominated by radiation. It means that mainly those fields which are massless or almost massless, which are photons and neutrinos, and then somewhere here take over. It was taken over by matter. It means the more massive fields were governing the evolution of the universe. It means that they were like the majority of the energy budget, energy density budget. So here we have baryons and cold dark matter. And then here we
recording in progress.
Okay, sorry for technical interruption. So today we are on the very right of this plot, where recently the evolution was taken over by dark energy, which is unknown what is the nature of dark energy, but again the evolution is different, and now it appears to be accelerated due to the dominance of this energy density component. Okay, so that's the evolution of the universe, and now how is it? Well, here we have it. We have like two let's say snapshots of the same diagram. It's today and let's say at the beginning of this diagram. So we see here. Well, what is important here is that we have like let's say about 5% of standard matter, what we know, like atoms and so on. Then we have 23% of dark matter, and the rest is dark energy. And if we would like to plot here what is the portion of neutrinos and photons, we would not even see it in this graph. It would be tiny, tiny part. It's written here. Today, we have 0.5% of energy density from neutrinos, mostly from relic neutrinos, cosmic neutrino background. And then we have even less, 0.01% of photons, mainly in the form of CMB, cosmic microwave background. These two relics. And the rest is basically given by this diagram. But if we look at the same situation from the point of view of not energy density but number density, how many particles are there, then we end up with a very different picture. That we would have neutrino number density would be 336 neutrinos per cubic centimeter. That would be a bit less than photons, which are 440 per cubic centimeter. And then the usual matter given by mostly baryons or let's say protons, you would have 8 orders of magnitude less per cubic centimeter in average, of course. Of course, at the Earth is something else because the matter is clustered, but in average it's this number. And for dark matter, which it is also different number. But it's again like dark matter also clusters, so locally it may be bigger number, but in average. Yeah, I guess so. This is assuming some mass of some mass. But I don't know which mass. But it's somehow. But I think I took it from other sources. I'm not sure. So this is my motivation, that the universe is full of neutrino, or let's say void of universe, space is full of neutrinos and photons, and all the other particles are much less. Okay, but of course, standard model predicts interaction of neutrinos and photons, but because it is not a three-level, property of neutrinos to interact with photons because they are neutron. It is predicted to be very, very small, and so this dynamics of two components of the universe is like in standard cosmology is considered to be no interaction between them. Basically, if you don't need it, it's completely negligible from standard model because it comes only as a loop effect. But here is an example which I like very much. I just dare to put it here. This example from 2014. Where even this tiny interaction of neutrinos and photons might bring some surprises. And this is one of them, but the surprise unfortunately is not like realistically feasible, but it's still very nice. And it motivates me to look in this direction. So I will explain what we are looking at. This is like neutrino as double beta decay. Without this green cross here, it would be like a mass mechanism, neutrino mass mechanism of Majorana neutrinos for this neutrino beta decay. But here, these authors, they considered an effective mass of the neutrinos coming from external magnetic field. So imagine that we would have isotope which is expected to decay by, or is decaying double beta, and we would expose it to external magnetic field. This external magnetic field, if there is magnetic moment of neutrino, then this external magnetic field interacts with this virtual neutrino here and produce effective mass. And now the question is, how big is this effect? And if we can somehow tune the values of the external magnetic field to have some maybe enhancement or some control of this decay. And they estimated exactly this, value of this effect, or the size of this effect, considering external magnetic field to be 1 Tesla, which is achievable in laboratory. Then neutrino magnetic moment of the order, which is today already excluded by experiment, but it is only 1 order bigger than the experimental limits today. And they assume this mass, sorry, this range of mass of neutrinos. And the result is that to actually, and that is actually they analyze this effect, and they realize that there is some resonance enhancement. There is some resonance, you know. If you tune the magnetic field to be like, first of all, you need a time-dependent magnetic field, and then you can tune the frequency of magnetic field so that you meet this resonance, and then you can have like many orders of magnitude enhancement of the effective mass field, and which would overcome, it would dominate completely the neutrino as a propagatory decay rate above the mass mechanism. And so they were estimating how big frequency they need for meeting this resonance. How is that? I think it's there appear denominator in the expression, and there is like it will be a propagator denominator if there is no magnetic field. But if you switch on magnetic field, there appears like other term in the denominator, and there will be derivative of the magnetic field in this effective mass. And then you can tune this term to cancel all the others. For the energy, typical energy, which is hundreds of a million. So you need to produce this effective mass of the order of hundreds of a million, I guess. Because for a resonance like that, you have to have a natural frequency of the system. I think it will be mass augmentation. Oh no, maybe not. Maybe it will be given more like with this wavelength of the neutrino, I think, because that dominates. Well, the neutrino is in the nucleus. The typical wavelength is given by the nucleus size, and I think if you want to meet this value. There is a reference, but simply they end up with the frequency. So you need to rotate the external magnetic field. This is a huge frequency, 10 to 23 hertz. So, unfortunately.
Yes. Yeah. Adam, may I ask a question?
Yes, please.
Look.
But we don't do it.
Excuse me? Can you hear me? Can you hear me?
Good question.
Yeah. Okay. Can you hear me? Yeah. Right.
Speak louder. Please.
Louder. And now better? No, not. You cannot hear, right? Okay. So just one question. I don't know if you hear me. This magnetic moment should be transition magnetic moment, because this is a magnetic moment violating Neptune number, right? So then this must be transition moment because it doesn't have diagonal matrix elements. So you need then, in this case, I understand that this is the paper you discussing, but this must also include the mixing of neutrino, right? Because this is the transition magnetic moment, right? Because well, for Majorana neutrino, magnetic moment, diagonal magnetic moment is zero, identically.
Yes, yes, sir. Thank you. I heard only the end of your question, but I understand the point. You are right. They are considering magnetic moment for Majorana neutrinos. It means transition moment, and for that they also include the insertion of the mixing.
Mixing, okay.
Exactly.
But it, yeah, but this leads to, yeah, right. But this leads to an extra suppression factor, right? Okay. Okay, yeah.
Do you have an extra question, Sergey?
No, it's okay. Well, but I just wanted probably more comment than ask, because well, but that there must be an extra suppression factor due to neutrino mixing, because this magnetic moment of Majorana neutrino should be transition momentum magnetic moment, right? There is no diagonal term, so then there must be transition of electron neutrino to muon neutrino, for instance, due to this interaction.
Yes, actually they take it into account. This result contains the
Okay.
So let me move to the
But
slide.
this
I have echo. I think I have echo. Sorry. Let's see. So so that was motivation a bit longer. Sorry. But what we have next is the let's say map of neutrino photon interactions. So in standard model, typically you can derive or not even the most common or commonly discussed neutrino photon interactions are in terms of so-called electromagnetic properties, and they are described by four form factors, which are magnetic dipole moment, electric dipole moment, charge radius, and anapole moment. And they can be predicted. Their values can be predicted from whatever model you prefer, but from standard model, they can be also predicted, and typically by this kind of diagram where we have one loop with exchange of W. So there is suppression of W boson mass square, and yes, and if we make prediction for the magnetic dipole moment, which is for direct neutrino the strongest electromagnetic property, then we end up with this terribly small value, which is 10 to minus 19 of Bohr magneton. Then we can talk about scattering of photons and neutrinos, like elastic scattering, which partially is described by these electromagnetic properties of neutrinos. But not only. Actually, the leading term comes from this diagram, which is not accounted in this electromagnetic properties, as you can see. Like here, this diagram is actually, you can imagine here that that the loops are actually the form factors which are already here, while in this diagram you cannot reduce it to electromagnetic properties. And in standard model, the dominant effect comes from this one loop diagram, which goes as 1 over mw squared, compared to this diagram, which gives you 1 over mw to the fourth power. And then we have, and then there is of course possibility to think about other amplitudes in standard model, where we have more photon lines attached to such loop. And then we have here like a map of effects of these interactions, which were in the previous slide. So I split it into, let's say, 2 columns and 2 rows. So here we have like basic processes, which comes from which comes from which comes from either like single vertex of electromagnetic properties, so 1 photon and 2 neutrino lines, or scattering kind of like neutrino gamma vertex. And here we have higher order processes where you need to take into account more photon lines attached to the amplitude. And in the first row here in blue color, you see actually the effects which are happening in vacuum. And in vacuum, there are no processes which are below this blue line. Okay. So here we have in vacuum contribution to elastic neutrino scattering, neutrino decay. So if this is thanks to non-degeneracy of neutrino masses, so the heavier neutrino can emit photon. Then we have okay, and as a higher order, for massless neutrinos, this process is actually the dominant one. This is interesting that for massless neutrinos, these processes are 0 in the leading order. So you need to take into account higher orders. Much more effects you can get in matter or in medium as a plasma effects and so on. So the most crucial one is the plasma decay, which is important for stellar cooling dynamics and so on. And there is much more the importance of this plasma decay important and is very big in astroparticle physics or astronomy and so on. Then we have effect which is predicted but not observed. It's spin precision in magnetic field, which is again for astroparticle physics might be interested to observe because there are magnetic fields in the universe which are floating there, and neutrinos can stream from supernovae, for instance, and on the way they can encounter such a spin precision, but there is no way today how to measure such thing. And then we have other processes and other effects like neutrino Cherenkov radiation, neutrino stimuli, induced neutrino charge. These are all effects which are only predicted but not observed. And similar things in this similar effect in the higher order as a higher order processes. And then we have here this this effect which I'm going to talk about in the following. Again, it's just predicted, not observed. And this is let's say bunch of effects when you stream neutrinos through, when you stream photons through neutrino medium. This might be relevant because, as we saw at the beginning, the universe is full of neutrinos and there is like neutrino medium, and you can ask the question if, for instance, there is some effect on the photons which propagates from some distant stellar object. So what is the effect? So basically here we have process like gamma goes to medium neutrino, scatters on it, forward scattering, and from that we can calculate the optical effects, which are at first is birefringence or optical activity, or also variation of index of refraction. So simply photon would be its phase velocity would be different from speed of light because of matter effect of Newton. Okay, so and this is what I was looking at, and so what is it? This birefringence of a neutrino medium. It was actually the first let's say, analysis of this effect was done by Royer in 1968, and it arises in general. Birefringence arises in electromagnetic media, and that's actually yes, such as cosmic plasma. So, for instance, we have cosmic plasma is mainly electrons, and if they are also coupled to magnetic field, they are producing so-called electromagnetic medium, and then the photons encounter so-called Faraday rotation. It means that their circular polarization, left and right, they got different index of refraction. So if you start with linear polarization here and propagate it to such medium, these two eigenmodes, circular eigenmodes, they propagate with different speed, and it results in a change of angle of the linear polarization. This is called Faraday rotation, and this is measured in astronomy, and by this method you can actually do some tomography of the universe and also reproduce the locations of magnetic fields in the universe. The description, the theoretical description of this effect is it is based on a non-zero, so-called parity violating part of photon polarization tensor, which of course in vacuum is zero, such part, and also in media which doesn't provide the parity violation. So this is a usual medium with no birefringence. How can you get the parity violation? You get it from, I guess it's because you have one more four vector available. You have actually not only the four vector of the photon in the medium, but you have also four vector of the medium itself. The medium is the medium, for instance, for Faraday rotation. The medium is electron plasma. What? A plasma, like electrons together with magnetic field, and this magnetic field polarizes somehow the electron. And this is like then producing like parity violent medium. And it is like because you have two four vectors at disposal, and you can contract it with this Levitch symbol, and you get parity violent contribution. But that's the other option. Like one option is this electromagnetic medium, which is what I said. It's electrons with photons, with magnetic moment. Sorry, with external magnetic field. external magnetic field is giving you it's like affecting the electrons, producing this medium to be, let's say, characterized. Maybe one can also think about really to make the parity transformation, but I was not thinking about it. I don't have it prepared somehow. But the other option is here written a chiral media, which means that you have this is clear. These are neutrinos, actually. So they do it without need of external magnetic field. They do it by themselves. Maybe we can discuss later or think about it later. You have more one chirality than the other. Yes, yes. Basically, all the equations what you will get from now is you have like neutrino anti-neutrino difference of density. So if you would have the same density of neutrinos and anti-neutrinos to 1h, get rid of the effect. And as the neutrinos are very chiral, so anti-neutrino has mostly chirality. So, and if you put into the formalism of the description of photon propagation, if you include this parity violating part, you end up with the, like you can diagonalize the propagator, photon propagator, and you end up with two modes, transverse modes, which are coupled via this parity violating part. And you can see if it is zero, then they propagate the same way. If it is non-zero, then they have this dispersion there. So both transverse modes will have different phase velocity. Okay? It means different index of refraction and different propagation. Okay. What was in the literature about this effect up till now is the following: that people studied really like cosmological or astroparticle situation when they were asking what happens to photons propagating through cosmic neutrino background. Cosmic neutrino background, assuming the density of cosmic background and also the asymmetry of cosmic neutrino background, which is allowed by the standard cosmology. And basically, they derive the formula which describes the effect, which is actually expressed where the crucial part where the information about this effect is hidden is this parity violating function. Right, but it's not imaginary part, which is it has but the imaginary part will be telling us that there is like it will be above some threshold, no? But not here. This is like very low energy effect. Very like this is like we are assuming now. I didn't tell him, but let's imagine like optical photon. and neutrino background. So it's just like all like slowly moving. Yeah, yes, yes. You need to place. I probably don't have to. But you know you need to, but this space is just like the evolution in the evolution operator of the evolution for the photon, and it's just this is like already here that the two walls will get different evolution phase, let's say. So they will propagate slightly differently and rotate to the polarization. So one needs to calculate this as a to get the reading the order effect, and one end up with some tricks, like assuming you know that. Well, I should say maybe first the other thing that. No, it's good. So if you calculate this diagram with yes, this is in vacuum. If you calculate this diagram in vacuum, you end up with this. Okay. It's not like you need to what you need to do to end up with this function, which is like polarization tensor coming from polarization tensor of photon. Yeah, I will explain now. This is you need to use this forward scattering amplitude, but then also to use statistical quantum field theory to close the neutrino loop and average over the medium, basically. Average over the real neutrinos from the medium. So you imagine that to get this function here, you close this loop, and here you don't put the vacuum propagator, but so-called medium propagator, which is getting which is given by density of the neutrinos. So basically, you have integration over the density of neutrinos. So this is like the statistical averaging of this forward scattering over this ensemble of neutrinos in the medium. So, and you end up with this. So here we have this difference of neutrino anti-neutrino densities. So we see that it is zero when there is no asymmetry. It depends on the k squared, which is like 4 momentum squared of the photon. So in vacuum, of course, like you would have 0. But here you should think that the photon is propagating in medium. So the neutrinos are already giving you this medium, and slight difference from 0, like of this k squared. But what then people did, and especially this Mohante, which was 1998, they assumed that this is also like sank into the cosmic plasma of electrons. So basically, then they put here for k squared, they put the plasma frequency of this cosmic electron medium. Plasma frequency squared. So due to electrons, the photon is moving differently from the speed of light. And this is given by plasma frequency of the electron plasma. So this is a bit like maybe a bit cheating, but it's not like proper way how one would need to do it. But there was recently recalculation of this effect with a much better approach, where they were averaging over also electron component of the plasma. You know, so not overcoming this difficulty to encounter the electron plasma, but they really included by this statistical quantum field theory machinery. And that was Dvornikov and his group, and now what are the results? And there was also, before that, I should say that after this result, they were also recalculating the pure neutrino effect, without electron component. And now the results are in this diagram. So here by that is this pure vacuum filled with only neutrinos, only C and D, let's say cosmic neutrino, and no electrons. Then, and what we see here in X and Y axis, in X axis is the photon frequency. So this is basically color of the light. So visible optical range is somewhere on the left, and to the right is harder and harder photons. So somewhere here is X-rays. Then what we have on the Y-axis, it's actually the this is the angle phi by which the linear polarization is rotated in radians. If you take the length of the propagation of photons to the Hubble distance, Hubble radius, so 10 to 26 meters. Okay. So this is like 10 to minus 6 radians for optical light. If the light travels like that radius of the universe, basically, which of course completely tiny thing, compared to Faraday rotation due to the intergalactic magnetic field, which is of the order, let's say 10 to minus 9, 10 to 10 radians, which is already measurable. Okay. This is important. So somewhere here we have measurable values. This is completely out of anything. But what is important that if you include the electron component, you are increasing the effects by 20 orders of magnitude. This line here is this result of Mohanty 1998, and then proper treatment of electron component increased it by other 3 or 4 orders of magnitude, 10 to minus 40. Okay. Good. And now we are coming, and we had an idea because what was important in this, what was important here as a lesson is that if you include some, let's say, refractive component, which is making deviation of the phase velocity from speed of light of the photon, then you are getting this immense enhancement. So we were asking the question, what if we let the photon pass through a really strong, optically powerful medium, which is for us, of course, something like glass or silicon or so on, when you have an index of refraction of the order of 1. But of course, you cannot make a cosmologically long glass or optical fiber, silicon optical fiber or so. So we need to go to like a terrestrial situation. So this is our thought, Gedanken experiment. Okay, we are thinking now about optical fiber, and let's say 1 meter long. We let the photon pass through like laser, in optical range. So let's say frequency of 1 electron volt, and then. Of course, if we expose it to neutrinos from cosmic neutrino background, it would be hard. We expect tiny effect, of course. So it would be hard to measure it because what can be in principle measurable is only the change of the effect, not the absolute value. So if we just expose it to cosmic neutrino background, there will be some effect, but it will be not measurable. We need change. So that's why we were thinking about the strongest terrestrial source of neutrinos, which is reactor. So we are placing the optical fiber to 5 meters distance from the nuclear plant core, and here we assume that the power plant is producing flux of neutrinos 10 to 21 particles per second. So, of the energy of several MeV, and we have gamma factor, this Lorentz gamma factor 10 to 7 because of this energy. And let's see what is the effect. And I said that we need change of this effect to intrinsic to measure. So there are two possibilities: either we switch off and on the power plant, or we rotate the optical fiber in this flux of neutrinos. And for that, we need to carefully calculate what is the angular dependence of this effect. Okay, so we did it. First of all, we needed, in order to calculate properly the angular dependence, we needed to correct actually the formalism which was used in the past to describe the photon eigenstates. Basically, there was not complete, like not completely correctly formulated the basis of the photon polarizations. So we corrected and we encounter, well, I will not speak about this because I didn't mention it before, but basically we encounter different angular dependence.
What are the measures here?
Yes, we would measure again the linear polarization, change of angle, direction of linear polarization. So we would produce the linearly polarized beam, and then at the end of the film, we would like to see if it moves a bit. Yes, yes. So I will not go into the detail of derivation of this angular dependence. I just want to say that if we would use the previously used formalism, we would end up with different angular dependence, and we have some arguments why it's not correct. So because that factor would lead even to imaginary values for some range of parameters. So that's why we think it was not correct, and this looks much better. And we have like arguments why it should be this way. Otherwise, this formula is very similar to the previous formula what I was commenting from Mohanty. So basically, here we have the coupling constants. Here we have this asymmetric factor of neutrinos, of neutrino densities, and then we have also electron mass squared in the denominator, and this is basically the k squared of the photon in the medium, in this medium. So it depends on the refractive index here. So that produces, you know, in the previous case, the k squared was very near to 0. Okay, the effect was very small in cosmological situation, very small, and it was almost like speed of light. It was almost like light k. But here, in this strongly refractive medium, we have k squared, which is of the order of 1 in the units of the lens. Okay, and our result is this number for this Gedanken experiment. So again, something not measurable, but we are getting better number than the group before on 1 meter. They were using Hubble radius. We are getting 1 meter. This incredible size reduction comes simply from basically from the Avogadro number, because in the cosmic plasma, what matters is the density of electrons, which are like strongest refractive component of the medium. So in the cosmic plasma, you have 10 to minus 4 electrons per cubic centimeter. Here you have Avogadro number of electrons in cubic centimeter. So there is like 10 to 26 factor just because of the density of electrons. And this actually is exactly this factor of refractive index. That would be the difference from refractive index of cosmic plasma versus refractive index of this optical fiber. Is 10 to 26. So that's why we could reduce this size of the. Okay, I don't know. I need to. When should I finish?
Take your time if you use it, 50 minutes.
I am already 50. So I try to be brief. Yes. So that was main result, and now what is the subsequent result is that we also ask the question: what would be the change of index of refraction for the laser in the same situation? Okay. So I will not bother you with this details. I just the expression is here again, like we derive it with all the details with the directional dependence, but in very like rough approximation of perfect uniformity, which means like perfect uniformity of the neutrino beam. You know that they are completely collinear and completely monochromatic, which is completely unrealistic. And this is the result, and there is some say angular factor here. This ratio here. We will comment it maybe later. And the result is even smaller. So the change of the index of refraction on this 1 meter distance is 10 to minus 65 times the angular factor, which is typically of the order of 1. So 10 to minus 65 of the change of index of refraction. That should be compared to advanced LIGO sensitivity, which is sensitive to 10 to minus 23 change of index of refraction, like effective change of index of refraction, because they are measuring really the length, not the index of refraction, but this is like effectively you can describe this change of index of refraction. So this is like completely, out of anything. But this angular factor, which is here, is promising or maybe showing, just pointing towards a possibility of having some resonance. If one cancel out this denominator here, okay, it can be made 0. But this is the problem that's the problem of this rough approximation of perfect uniformity. Because if we would do it like more realistic, we should basically average or convolute this corresponding amplitude. We should convolute it with this distribution function of the neutrino flux, basically. It will be smeared, this resonance will be smeared. And if I'm writing somewhere here. Yes, this is, it would require the collinearity expressed in the cosine of the angle, of the photon and the neutrino flux. Then the dispersion of this angle should be less than this gamma factor. This gamma factor is in our situation 10 to minus 12. So we would be like completely like okay, we would have 10 to minus 6 10 to minus 6, better than 10 to minus, smaller dispersion of cosine of the direction, smaller than 10 to minus 6, which is I think still like out of anything. And that's only to get at least some visible, some trace of the possible resonance. The enhancement would be still like maybe only factor of 2. But the more uniform flux you would have, the more profound would be the resonance. So just basically final remark. In the last slide, it's that motivated by this work, we just want to switch to neutrons, because neutrons, they have much stronger magnetic moment, much stronger electromagnetic interaction, and maybe estimate the effect, the effects which we were talking about, estimate it for a similar situation. So if we would have like a source of neutrons, there are some available sources we have on the Earth. For instance, there are some neutron fluxes up to 10 to 50 neutrons per second per centimeter square. And then we would like to estimate what would be the effect on the photon propagation through such medium. The very rough estimate, which is based on this neutrino result, just putting other numbers there, is that the change of index of refraction is 10 to minus 31. And so for neutrons, it's like 34 orders of magnitude stronger, but still very far from advanced level. How many? 8 orders of magnitude, but only 8 orders of magnitude. But we didn't estimate yet the birefringence effect, the Faraday rotation for neutrons, and this is like our future work. And also what might be interesting is to consider similar effects for dark matter from dark matter in models where we have so-called dipolar dark matter, which has some magnetic moment. It's not excluded from experiment. And also one needs asymmetric, fermionic, asymmetric dark matter. So this is like a very narrow class of dark matter models. But it might be worth to study. But this we will see. Okay, so that's all from my side. And thank you for your attention. I hope it was nice to
Thanks for the speakers for the very complete talk. Question from the audience.
You mean the one of the first slides or this resonance? That was.
Frequency of 10 to 23 hertz. Yeah. So, well, if I multiply that frequency omega times h, I get the energy of 110.
Yes. This is exactly what we are talking about. The resonance condition has something to do to cancel the denominator in the formula, which I'm not showing it here, but this formula is basically the denominator in the formula comes from neutrino propagator, and this neutrino propagator contains like energy minus or energy square minus mass square if there is no magnetic field. If there is magnetic field, then there appear another term. Like if for the instead of mass, you would have something like probably mass squared plus plus some magnetic plus some effective mass from the magnetic field. Maybe. So, and you need to cancel out the energy, not the mass term, but you need to cancel out most of the energy term, which is in the nucleus. For it, nucleus has size of Fermi, and that scale corresponds to hundreds of Fermi. So that's exactly if you multiply just this frequency is finish.
Sergei was also a person of this said we need some mixing transition. So how do you see here with electron? So
yes, it's a you need electron number you need electron number violation. So that's why you need Majorana neutrinos. And for Majorana neutrinos, the so-called diagonal magnetic moment is 0. It means that the electron neutrino photon doesn't exist. So there is only like off diagonal, so-called frame of diagonal, so-called transition moment, which is like electron neutrino, muon neutrino photon. And so that doesn't help you here because you need to close it with electron neutrino. So you would have electron neutrino, muon neutrino, and here you need to convert it and oscillate it to electron. So that's why there is insertion of the mixing matrix, contact mixing matrix.
an extra factor to question.
Yeah, but I think it's not so terrible. Like, this is not sure. Yes, I would say that it's cosmetic. Interactions. But in cosmology directly, well, well, this is actually my main motive, my most secret motivation to basically search for options that cosmic neutrino background would not be in such innocent state as it is formulated in standard cosmology. In standard cosmology, neutrinos are the cosmic neutrino background is just like let's say dust of neutrinos, non-interacting neutrinos, boring. So if there is like, there are some works which are speculating about some neutrino condensation formed due to photon interaction. So we can discuss it also later, but it's like not convincing, let's say. But of course, if you go back in time, then there might be some stages of the universe where it would be important. But again, standard cosmology, I think, doesn't need to take it into account because the interaction of neutrino photon interaction become strong enough in periods when other interactions are again much more important. So this would be a cosmetic again correction. I'm not aware of this interaction to be relevant for standard cosmological scenarios, not only one. No.
More questions from the audience? The people that are connected in Zoom. Any questions? If not, we the thickness of the device and the code and we need to the
Switching it. Ah, now it's well this.